Good day, physics students. I apologize for the atypical situation we find ourselves in today. As I said in the email, I'm just waiting on a test result, and as an overabundance of caution, we're doing remote today. My plan for today is watch this video, which will contain all the information that we would have gone over in class. And then I will be in a Google call room that you may hop into at your discretion between 11 and 1 p.m. because that's just the time slot that I would normally be teaching this class anyway, between my two sections. Watch this video, be working on the homework, be looking through the notes that this video is about and pairs along with, and hop into that call during those 2 hours if you have any questions, if there's a specific homework problem you want us to look at together. And hopefully we'll be back together physically on Friday to continue talking about sig figs and also to talk about the geometry questions on the same assignment. Today we're just going to talk about sig figs, and all of this I expect to be review for you guys. So we're just going to look over the sig fig rules to refresh on them and look at a few samples together. So, there we go. So, I have uploaded notes on significant figures to the Google Classroom. Do please take a look at those. The notes pair along with what I'm saying here. I'm going to be going through the slides as we go. And significant figures represent precision in measurements. You can take any two numbers and put them into your calculator and get a number that has, if you divide 7 by 3, you'll get 2.33333 repeating ad infinitum, on and on and on. But not every single number that you multiply is precise to the same degree as every single other number. Some tools in the scientific world simply measure better than others, which is why we care about the precision of those tools. The more precise your tool, the more certain you are about the number. The less precise about your tool, you need to state that you don't really know for certain this number you only know it really to a specific degree. And the significant figures are just to tell us which digits in the number are the significant ones that we really care about. So, quick sample. This is slide 2 of the notes. How many sig figs would be in each of these numbers? And they're all pretty similar numbers. For the first one, we've got 10,000. The second one is 10,080. The second one is also 10,000, but we've specified it as 10,000.0, which actually does matter. We're going to look at the rules for sig figs in a second, but go ahead and get in your heads how many you think each one is. You can pause if you want to think about it. But 10,000, as it's displayed, just 10000, only has one significant figure, because the rule is to the left of the decimal point. Non-zeros are always significant, but to the left of the decimal point, zeros themselves are not necessarily significant unless they are between the integer numbers. So in this particular number, everything is left of the decimal point. We're only given the one non-zero number and a bunch of zeros, so only that one is significant here. The second one, though, the 10,080, the 1 and the 8 would both be significant, but zeros that are between significant digits are also considered to be significant. So we have 4 significant figures in the second one, and then in the third one, it is the same number as presented as in the first one. It's still 10,000, but when you specify the decimal point and then continue onwards, zeros after the decimal point are considered significant, typically speaking. And so since that 0 is that 1 0 after the decimal point is significant, that makes all the zeros between it and the other significant digit to also be significant. So by adding in that guarantee of precision, that guarantee that we know this number to the 10th place, that makes all the other zeros significant, because we know for certain, based on that measure of certainty, that those numbers are zeros. So within these notes, we have the rules for determining the number of sig figs in one number. And these are just the rules for if you are given a number, if you are given a measurement, trying to figure out how many of its digits are significant. There's different rules for figuring out if you calculate a number, which digits of it should be significant. So these are the rules for if you are given a number, you're looking at it, and you're trying to figure out how many of its digits are significant. So the rules are non-zeros in a number you're given are always significant. So back on the previous slide, we had the 1 and we had the 8. Those are automatically significant. Next rule, all zeros between significant digits are significant. We see that on the second one there. We had 2 zeros between the 1 and the 8. The 1 and the 8 were both significant. That makes those 2 zeros significant. The number of significant figures is determined by starting from the leftmost non-zero digit. Okay, sorry. Even when I'm lecturing remotely, I need to take a minute to drink some water. I apologize. The number of significant figures is determined by starting with the leftmost non-zero digit. So by leftmost, that's all the way to the left from the decimal point. So as far to the left as the number goes. That one is the most significant digit, the most significant figure. We have a sample here. You do always have to start with the leftmost number. So I'm going to exit the presentation mode here. This is where the rules can get kind of fuzzy at times, and I apologize. Even though these 2 zeros are after the decimal point, they are still to the left of the first significant digit. So this 4 is the first figure that isn't 0. This 4 is the first significant figure in this number right here. So we consider this 4 to be the first significant digit, and all of the significant digits need to follow it. They can't precede it. So the 4 is the most significant digit here. The 2 and the 5 are automatically significant because they're not zeros, and the 0 between them counts as significant as well. So it's important to note that only these 4 digits here are significant based on these rules. And this can make sense if you envision this number instead in scientific notation. Because in scientific notation, those zeros in front of the 4 don't exist. This is one reason why we use scientific notation. So the first non-zero digit is the most significant digit, and every other sig fig has to come after it, not before. The leftmost, the last significant digit, is the least significant digit. If no decimal point is present, the rightmost non-zero digit is the least significant digit. So in this number, where we don't have the decimal point to guarantee accuracy to the 10th place, the accuracy stops at this last non-zero digit. So we have 2 sig figs in 5,800, and the least significant figure is 8. Using these rules, take a quick look at some of these sample questions here. A couple different types of numbers we've got here. You can pause and think about each one for a sec. And moving on to the next slide, we have the number of sig figs in each. I'm actually going to come out real quick. For this, can you even see my cursor on OBS? Yes, you can. So, first number here, all non-zero digits left of the 0, they are all significant. Here, the 0 is before the first significant digit, so it doesn't count. We also still have 5. Here we have all non-zeros, so 6. Fourth one, the 0.0023. All these zeros are to the left of the first significant figure, so they don't count. We only have 2. Next number, the 0.02300, is very similar to the previous one, but we've added 2 more zeros after the least significant figure. Since these zeros are after the decimal point and they are still proceeding down the order of significance, we're going still from left to right, from most significant to least significant. Because they're after the zeros, these do count, because they're after the decimal point, and after we start counting sig figs, these are also now significant. We've guaranteed the number down to the 10 hundredth, thousandth, down to the 100,000th place. The fourth to last one, 1.009, has 4 sig figs because the 1 and the 9 are automatically significant. The zeros, therefore, also count. Similar kind of case with 230,000 and 4. These zeros are between sig figs. The last 2 numbers are essentially the same number still. We have 100, which is only 1 sig fig. There's no decimal point here, so we stop counting at that first one. And then the last one, 1.00 times times 10 to the second power. In this number right here, the 1.00, because those zeros are after the decimal point, they are significant, so we have 3 sig figs in this one. So all these samples, all these rules are for if you are given a number. Given a number and you're trying to figure out how many sig figs are in it. This is important because when you are given numbers, you then usually have to do something with them, like add, subtract, multiply, divide. And there's rules for how to figure out the number of sig figs in your answer based on the number of sig figs in what you were originally multiplying, or adding, or subtracting, or dividing. So, as a refresher on these rules, there's a different set of rules for adding and subtracting, and a different set of rules for multiplying and dividing. Adding and subtracting. We've got 3 sample numbers here. We've got 32.01, 5.325, and 12. When you are adding and subtracting, you actually don't look at the number of significant figures. You look at which number is the least precise. Our first number here, the 32.01, is precise to the tenths place. We have a significant figure in the tenths place, and that's the last one given. The second number, 5.325, is significant to the thousandth. The first number was significant to the hundredths place. I misspoke. The second number is significant to the thousandths place, which makes our second number more precise than our first one, because its region of precision goes to an even smaller decimal value. But the 12 is only significant to the ones place. There's no decimal values given. This number only has 2 sig figs, and they are both before the decimal point. So that makes this number the least, this is the least precise measurement here. So it's the one we're going to base on. We are only able to report precision to the ones place in our answer. Whoops. So if you put these 3 numbers into your calculator, it will give you 49.335. We only have precision to the ones place, so the official precise answer is 49. Now, I do usually like writing out the full number. What one might do if you want to write the full number and then indicate how many of its digits are significant, I like to underline the digits that are significant, or occasionally overline them. I just can't do that in PowerPoint. As long as you put a line under or above the significant digits, that indicates which ones are significant, and you can add the rest still if you just want to show them for your own notes. So, the rules for adding, subtracting are least precision. Not least number of sig figs, strictly speaking, but least precision. Multiplication and division is about the actual literal number of sig figs that is present. So, for example, we have these 2 sample numbers here, 25.624 divided by 25. The 25 has 2 sig figs, while this number has 5. So that makes the 25 the least precise. So if we multiply or divide these numbers, the answer should be reported as having 2 sig figs, as with this 25 here. So your calculator will probably might give you something like this, but we want specifically 2 sig figs. Now, the answer is going to come out to about 1. So 1.0, those are our 2 sig figs. Next slide, this is slide number 8, has some samples on it. And these samples are already worked out. It's just up to you to figure out how many sig figs are present in each of the preceding numbers and then the significance of the answer. So you can take a second and pause here, look at these numbers, and the answers are on the next slide. So for the first one, 32.27 has 4 sig figs, 1.54 has 3, so the answer should only have 3 sig figs, counting from left to right. The next one, 3.68 divided by 0.07925. We also only have 3 here. The first number has 3, the second number has 4. Keep that in mind, the second number here has 4, so the answer should only have 3. Moving on, our first number in the third sample here has 4 sig figs, 1.750. The 0 is after the decimal, so that is counted. The second number, we have 6 sig figs. The first 0 doesn't count because it's before the first non-zero digit, but the zeros afterwards do count. But the second number has less sig figs than the first one, so the answer should only have 4. So similar and similar, down we go. So use these as samples to refresh yourself on the rules themselves. Now, that's the end of the slides, because the slides for this are just to remind us of the significant figure rules. And these will be used on the homework assignment for this week. I'll just find it here. So this is our, forgive me everybody. So this is our assignment for this week. We are on week 5. I apologize for the notation. I ran this copy off last week, and I don't want to modify it any further so that everyone has different copies. So it says week 7, but we're really on week 5 of material. I apologize for that inconsistency. And the bulk of this assignment, at least the first half of it, is about sig figs. So the first 10 questions involve significant figures. The second set of 9 questions are more geometry-based, and we'll be looking at those together on Friday. And for today, please go ahead and look at the first 10 significant figures problems. These all factor sig figs in, and what I've done is I've gone ahead and, because we would normally work them together on the board, I've done the first 5 for you guys, because they are also good review. They contain good review material. This particular document that I have here is uploaded to the Brightspace page along with the notes, and I'm going to put the homework file there as well. These are the first 5 questions from the assignment. So, looking at these briefly with each other. First question, using the rules of precision and sig figs, can we calculate the following? So we're going to look at the first 5 together real quickly. First question, we are adding 1.2 to 2.345. And now this is addition, so it's less about number of sig figs and more the range of precision. Our first number here is precise to the 10th place. Our second number is precise to the tens, hundreds, thousandths place. So our answer should only be precise to the tenths place. So you can put these 2 numbers into your calculator. It should give you about 3.545. Of all those numbers, we are only precise to the tenths place. So our precision tells us the answer should be about 3.5. Now again, if you write out the full number that your calculator gave you, that is fine. Underline or overline, you can put it above or below, the digits that are significant. So if you wrote out the full 3.545 and then underlined the 3.5, that is A-OK. You are just fine. Number 2 is multiplication instead of addition. So we do need to count sig fig numbers specifically this time. 1.2 has 2. 2.345 has 4. So you pop them into your calculator, you multiply them to get 2.814, and the answer, of the numbers that went into it, the 1.2 had fewer sig figs. It only had 2, so our answer should only have 2. So we underline the first 2, and if you wanted to, you could write the precise answer as 2.8. In the third problem, you know what? I might have messed my work up here. I apologize. I might have jumped the gun just a small bit. I did, actually. I did. Okay. I'm going to have to amend my work here just slightly. This one has subtraction and division. So first we're going to subtract these first two numbers here in the absolute value, 3.45, which is precise to the hundredths place, and 3.21, which is also precise to the hundredths place. That means that whatever we get from this first operation is precise to the hundredths place. So that's going to give you 0.24. Now, that is technically what that would give you, and I'm going to show my calculator real quick. The 0.24 is only precise to the hundredths place. So there's only 2 sig figs here, actually. So we're then going to divide by 3.21, which is going to give us the number on screen. But, and I apologize, the work on the paper is a little off. I made a mistake. Sorry about that. Where's my finger? The 2.4 has 2 sig figs. We divided it by a number with 3 sig figs. That means the answer should only have 2 sig figs. So, what I have here for 3 is just slightly off. The number's the same, but the answer should only have 2 sig figs instead of 3. So only the 7 and the 4 here are significant, so the final most precise answer should actually be 0.075, and then cut it off there. I apologize for that. Number 4 is division, but it is employing a specific kind of rule. And generally, if you were given a whole integer value that is between 1 and 10, we consider that number to have infinite precision. If you look at the question here, you and your 2 brothers are fixing a roof on your chicken coop on a hot summer day. You have approximately 5.25 liters of lemonade, and you want to split it evenly between you and your siblings. You and your 2 brothers, that's a total of 3 people. That 3 is considered to be infinitely precise because there is specifically 3 of you. This is not going to count as 1 sig fig. This number has infinite precision. There is definitively 3 people, end stop. That number is precise all the way into the however many decimal values you want. So this 3, because it is a definite whole number, is infinitely precise, which means it technically has infinite sig figs, and it doesn't really factor into the math at all. So our other number, the 4.25, is the one that is going to affect the significance here. So this number has 3 sig figs. Our answer should only have 3. And again, if you have issues determining whether or not an integer should be infinitely precise or not, if you look at the question, there's definitively 3 people here. That is a precise, physical, finite number. There's no chance of there being additional, like, fractional amounts of people present. So that's why the 3 is considered to be infinitely precise. I also want to look briefly at number 5, because this is technically not addition, multiplication, subtraction, or division. This is the cosine operator. And for an operator like this, count the sig figs and the answer will have the same number of sig figs, because this operation is doing a series of steps on that number. The precision of the answer depends on the precision of what you put into it. So this number, 53.23, has 4 sig figs in it, so our answer will have 4 sig figs. So, and this document is on the Brightspace page. I may upload a slightly amended copy because I did make a minor mistake on number 3 here. I do apologize about that. I do apologize. Whoops. I'm going to be sending out the Google Classroom code, and I'm going to be in that classroom call until about 1 p.m. You do not have to join the call, but I will be here sort of like study hours. Use this information to begin your homework. You got the first 5 ones here. Begin looking at the next ones after that. And jump in if you have questions, if you want us to look at something specific together. But watch this video first. That will also be summarized in the email I send out. Thank you all. Jump in with any questions you have, and hopefully I'll see you in person Friday. Keep checking your emails for more information. Thank you, and have a good and healthy and safe day.